when something doesn't work, what we do every time, we run explain command. So in this talk by Aivars, he will explain us how to make it correctly.
Yeah.
So.
OK, thank you. So who is a developer here in the audience? OK, so this is mostly a talk for developers, so let's go. So I used to work close to 19 years writing C++ and then raw SQL with Oracle databases, and we went through like a lot of disk technologies and tried different setups to make it fast, and then eventually we got to SSDs, and then we thought, oh, well, now it's good. And I don't have any work, so now I work for another company. We're using Python, ORMs, so Django, and our database is Postgres RDS running in AWS, and guess what? We are still tuning the queries. And so this is a story about how I tuned the kind of live search feature, so where you type some characters and database immediately displays you some possible results. So if you want to get the correct answer to how do I make my queries faster, well, typically it's something like, well, it depends. So I don't want to give you like, well, depends, so I will give opinionated opinions. And so if it doesn't work in like 10% of cases, or you find some corner cases that, OK, so that happens, but this is like for a more broader scope and for, let's say, 80% of your code. And first, let's look a bit into the theory. So the data inside tables and inside database is organized in database blocks. So typically it's 8 kilobyte blocks, and they are kind of laid out sequentially. So whenever you are searching for the data, you do a kind of sequential scan. So it gives you linear algorithm for retrieving the data. And since I'm talking to developers, I like to have this mental model of the programming language. So for that, so in Python, it would be to have a list of some records. Now, obviously, linear access is not that great. So therefore, databases implement indexes to speed up the lookups. The kind of most famous or most common index is called B-tree index. So it's not binary tree, it's balanced tree. And there are many variations of that. But the idea is that it has this tree structure. And then when I have to look up some key, so I want to look up key 18. So I start at the root. I look for values that are the greatest value, which is less than or equal to what I'm looking for. So in this case, it's 15. And this gives me a pointer to the next tree level. And then I scan through the kind of second level, and then I find that, oh, OK, so the value that is largest value that is less than or equal to 18 is 17. And then I get into the leaf node, where I find my key 18. And then it has data. So this data for Postgres is it's the tuple ID. But I mean, there are some databases like MySQL, which actually store the whole row in this place. So once we get the kind of address of the tuple, I can go to the database block and retrieve the interesting records for me. Again, so in practice, because Postgres is having this vacuum stuff and not overwriting data in place, so this gets randomized. And I mean, it's a complete mess. And again, in Python, so I'm using a Python dictionary. It's not completely correct because indexes are trees and the Python dictionaries are actually hash maps, but it will give you a good enough idea of what is actually possible and what is not. So it contains the keys, and then it contains a kind of list of record IDs that map to this key. So something like that. And Now the question is, how does database decide to use index or to do this linear scan of the table? So it boils down to some cost parameters. So I would say the two most important are sequential page access cost and random page access cost. Then there are some costs related to CPU, but if you check the numbers are like really 0.0 something or even less. And compared to the page access, it's like really nothing. So sequential page cost is 1, so it's the kind of base value. Now the random page cost by default is 4. If you read through documentation, it actually says it's actually closer to 40, but we assume that we will get 90% cache hit rate, so therefore it's 4. And the documentation also suggests to set it to 1.1 for SSDs. Now the question is, if you are using AWS and RDS, so what is the cost of random page there? So it was in the previous talk. It's actually 4. It's the same as the slow spinning disks. So today I learned that there are some cloud providers that have adjusted this cost. But I mean, the databases in cloud work as if they were running on a slow spinning disks. So now, given these values, so let's say I want to retrieve keys from 17 to 21 from the table. So if using sequential scan, so I have 8 blocks. Each block, retrieval of each block in a sequential way costs exactly 1. So it will cost me in total 8. And I have retrieved all the keys. Now, if I do the same for index, remember that this index has this randomness. And I'm not looking at how much it will cost to scan through the index itself. I'm just looking at the base level of accessing the data. And because this is random access, I have to pay random page access costs. So for key 17, I fetch 1 block. It costs me 4. I fetch another block. It costs me 18. So again, 4. Another key. And now already I'm above what like simple sequential scan would cost. So this is like the basic idea. And then from that, obviously it follows that if you want to access a single record, then it's definitely faster through index. I mean, 99.99% of cases. And accessing all table records is faster through table scan because, I mean, it's cheaper. And then obviously somewhere in the middle, there's this perfect balance. Most materials say that it's like a single digit percentage. So it might be, I don't know, 3, 4, sometimes 7, depending on the source. But I mean, it's a single digit. And it boils down to this difference between sequential access and random access. So it's already like, just by looking at those, the percentage would be 25%. But if you account also for costs for accessing the index, so it goes down into single digit. And it would be fine, but I mean, databases are often bad at estimating what percentage of records they will read, so they often choose the wrong access plan. Now, so that's the theory. So now it's time to practice. So I will be using Django. I will show also the plain SQL. So if you do not know Python and Django, so it will be easier to follow. I start with 2 tables. So I have member table. What's important there is a name. And I also create index on it. There are some documents, 3 possible document statuses. And I have documents which are linked to members. And I have status of the document, and then I have some like arbitrary JSON field with whatever there is. So in Postgres, so it creates like tables like this. So it adds the unique like primary keys, and then takes care of creating all the indexes. So I'm not showing that, but it's there, trust me. So now I filled this with, I started, I think, with 10 rows. Then the execution wasn't as I expected, so I had to add more rows. So that's the one takeaway, that always try to do query tuning on the like realistic data sets. Otherwise, you will get it wrong. And then for Django, so the way how you do this query set explain, there's the wrapper function, but in reality, it just executes this query. So if I do in Django, so this print member object filter and explain, it's the same as executing explain, select, and star, and then the real query with conditions. So here it is saying, since I created an index on the name, it will be using index, and the index condition will be like the name equals to the input parameters. So this is like a simplified output. I actually prefer to use analyze. So what does analyze? Analyze actually executes the query. So be careful if you are tuning some slow queries in production, so you might bring your database down. But the best things is that the database actually reports what is the actual execution time, not just like some theory how it would like to execute it. And then along with the estimated cost and estimated number of rows, it prints the actual number of rows that it returns. So that's like to do the sanity check of like database estimation and reality. Yeah, and then, so we do not have an index for that, but there's this iExact thingy in Django, which basically does case-insensitive search, and Django implements that as taking uppercase of the field and then comparing with the uppercase input. And since there is no index, it actually, the explained plan says that it's trying to filter rows by this condition, and it's doing sequential scan on the table, so no index is accessed. For me, if I look back at the Python, so I have, oh yeah, and the main question is, I mean, I did have an index on the name, but I didn't have it for the upper. And why doesn't it work? So if you have, like, say, a dictionary with these normal case names, and you want to do like a case-insensitive retrieval of the value, well, there's nothing like that in the Python dictionary to do this kind of access, and the only way would be just to do like a linear scan through it. So in a nutshell, so whenever you see sequential scan on some table, so this is going through doing linear scan on a table, and then filter. So here the explain tries to tell you what kind of index the database is looking for, and if you see index scan using, so it's yes, it's oftentimes what we want, just going through the index. Now, just to a bit more expand on these indexes, so we had this document status with 3 possible values. So on purpose, I created the documents with status unknown, and it is around 5% of the data. So now when I do query, if I'm looking up the exact value, so where status equals unknown, I get a very good index scan, and it matches on the index condition, everything is fine. However, it works only like for positive expressions, so equals, greater than, or less than. It doesn't work for inequality. So if I want to, remember I had 3 values, and I'm looking for documents which are not valid and invalid. So basically I'm looking for documents which are in status unknown. Database doesn't know that, so it has to do like sequential scan on the whole table to filter those out. So indexes do not work for negative expressions, and kind of a quick fix how to do is to transform it in application code. Okay, just in Python, so imagine if we had dictionary with 3 keys, and we can't like query, give me a key which is not one of those, so it leads to like really scan through the whole keys. So how to make it positive? Because application knows all the possible values of documents, so you can take all the possible values, subtract those that you do not want to see, and you get like a positive expression, so the values you want to get. So here it gets status is unknown, and since it's a positive expression, then the database can use index, and it's fast. And yeah, so let's build some more indexes. After all, we need to do some live searching. So first I want to fix this case-insensitive queries. So I see that the database is looking for condition which says upper on the name. Therefore, I must create an index on upper of the name. So the Django way is like this. So it's pretty similar also in plain SQL. So I create index for the exact condition that the database is looking for. And the resulting index is something like that, that all the keys are kind of translated to uppercase, and then if I get by uppercase, I mean the search actually works. And yeah, indeed, so by creating this index, so I have this name upper index, it's used, so everything is fine. So let's move forward. So what I want to achieve is to, I don't want to force users to type the correct case for the letters, so whatever user types, it's fine. So I want to do case-insensitive search, but only on the partial word. So in Django, it has this I contains. In plain SQL, there's this keyword named like. And the query that Django generates behind the scenes is this upper on the name is like upper on the input. And no wonder, so, I mean, it can't find the index for this. And the thing is that we have a B-tree index. And if we think about dictionaries in Python, so we can't retrieve from a dictionary something matching a partial key value. So there's no such feature. So how to solve this? Postgres has these gin indexes, and together with the trigrams, I mean, it delivers the result. So how does it look like from a programming language perspective? So the actual value stored in the column is first broken up into 3-letter strings. So it creates all possible 3-letter strings of like consecutive letters. And then it stores, creates an index of these 3 letters mapped to the actual values. And then whenever we are doing a search, we retrieve the kind of values for 3 letters. I mean, each 3-letter combination from the input, then combine the result, and there we get it. So, I mean, it's a bit more complicated, but it works. To get it working in Django, so you have to add some magic, like Postgres package, then you can create these specialized gin indexes, so it looks like really ugly in Django. And if you look at the plain SQL, so it's like really easy. So it's not like, it's pretty like you use like using gin and then specify the column condition and then give this trigrams operations. And yeah, and for Django, for all this to work, you must also create this PG trigram extension. The upper part is how you do it in Django, and the lower part is how you do it in plain SQL. So I did this, I created indexes, but the query is still not using the index. Any ideas? No. Actually, the fix is to analyze the table. So I added new index. So sometimes it works, sometimes it doesn't. So every time you do something, just run the analyze so you don't get these random outputs. And yeah, so now this is fixed. No, this is working. So this kind of, it takes the input and does uppercase inside the query, and so uppercase on the name as well. So now in theory, so if I wanted to do like case-sensitive search, it's not able to use this index. So because it actually doesn't have this, it's looking for a condition where it's the plain name, it's not the upper name. And this is like a bit, this is one of the places where frameworks shoot you in the foot. Okay, so first, so why it's not working? Because we have these keys in uppercase, and then if you try to do some lookup on some random case, of course, it will not find it. If you are not using frameworks, then you could do something like that. You create an index, and there is no need for doing some upper magic or anything. You can then do a query, and you say, like, so this kind of case-sensitive search, and it works, so it uses index. And then for case-insensitive search, you have to use this I-like. And specifically for these indexes with trigram operations, it supports I-like on the indexed value. So, but yeah, the problem is that your frameworks, in my case, it's Django, it still generates this query that is applicable for all databases. So it puts upper on the name and upper on the input and uses like, not I-like. So let's do some JSON. So I had the JSON document. A convenient way in Django, you can just pretend that it's structured data. So you can type data, document number, contains something. It gets translated to query again, so because it's I-contained, so it's case-insensitive. It looks up JSON field from the data column and looks for the field name document number, and then it looks for the string. So, and of course, there's no such index yet for this column, so let's create the index with Django. And so this is like really, really, really ugly. So this was found out by trial and error. So Django doesn't warn you, it just doesn't work if it's not correct. But I mean, I got it working. So index is created, but however, there's no improvement. Any ideas? I did analyze the table. So again, this is a case where frameworks shoot you in the foot. So if you look at the indexes, so I looked at the actual index being created and the explain plan that is being executed. Pay close attention to this part. So one of them says retrieve any JSON object having this key document number. So it might be array, it might be another JSON object, it might be a number, it might be a string. The second one, retrieve document number string. So in practice, they are kind of the same, but for database, strictly speaking, it's not the same. And so at this point, I kind of gave up on the database, so it doesn't create index consistent with the query it creates. So I went and fixed the index manually, so I added those two greater than signs, created the correct index, and now this live search works, it uses the index. And at that point, I thought, okay, so I got the indexes working on all the fields needed. It should be great. Let's combine it together into live search. So live search, in practice, it was something over 7 tables. I managed to reproduce the same issue with only 2 tables. So what I'm doing here, I'm looking for all members which have these 3 letters in their name, or they have a document and document number contains this 3 letters, so something like that. So in the kind of plain SQL query, it creates a join, and then it does this one condition or the other condition. And this is where Postgres surprised me. I used to work in Oracle. I don't remember seeing anything like that. And the thing is that it didn't use any index. So and in fact, so what it did, it kind of scanned both tables, produced intermediate result, and then did the filtering on the probably some temporary data without using any indexes. So I would expect it to use at least one index, so it did not. So turns out there's a typical kind of well-known fix for that, for Postgres. Yeah, and so it's just being silly, sorry. So the way you do it is that you do replace OR conditions with unions. So I collect member IDs for one condition, then I collect member IDs for other connections, so it results in this long and scary query that actually accesses member table twice, and then I do it one more time to actually retrieve the members. So, and this looks like really, really scary. But if you look closer, so first the execution time improved 4 or 5 times, so that's good. Not perfect, but good. It actually is using index on the document, JSON. It's also using the second index on the name, which is great. And yeah, it's just that the query is ugly. And there are further improvements. So actually, if you think about it, you do not need to join the members table for the document. So you can just retrieve the member ID from the table directly. So as a result, you will like read through the member table only twice. So once to gather the IDs and the second time to retrieve the data. And so quickly, and why I'm talking about this, so there's a study that came out and it conveniently supports my, my point. So they investigated what are the typical issues with kind of these Ruby on Rails and Django applications, and the missing database indexes came as number 1, so it scored 30. To be honest, like n+1 queries scored 29, so a close contender, but I mean, still missing indexes win. And yeah, that's it. That's why you should properly index your tables and use explain plan to consult what kind of indexes you actually need. So I have my experiments with Django query set on the link, and this QR code is supposed to take you to the feedback for this talk. Thank you.
So now we are inviting you to ask questions. Just raise your hand and we will come to you.
You show us the calculation for the index random access cost, and you said, if I remember correctly, it was 4, which accounts only for the last access to the table.
Yeah.
Do you know why doesn't Postgres also include in the calculation the B-tree traversal?
Yeah, I think B-tree is also kind of random access. There are, I mean, different calculations to retrieve I think the root node, and then, yeah, I think it's mostly random access, but then it also adds the CPU calculations, how much it costs to compare the keys, but I mean, it's like really small.
Thank you very much for the talk, very nice talk. At the beginning, you talked about the coast configuration numbers. Have you ever found yourself tuning these, or under what circumstances would you touch these?
So I'm not touching these. There are some database experts that have written about this, so it kind of, the costs kind of suck that they are like that, but in order to get consistent results in all environments, we kind of accept that. Yeah. I don't know. I mean, so far, I got good enough results by just creating indexes and tuning queries. So at least at current companies, I'm not like pushing database to the limits as I used with Oracle before. So let's leave that for, I don't know, some DBA wizards.
Thank you.
If you've got to implement a text search across multiple columns on a table, would you rather create 3 separate indexes So each, or one for each column? Or would you create a computed column and then add an index on that one column?
That's a good question. So we used to do that back in the days with Oracle. So we had these kind of manually computed columns which stored the text in uppercase, so we didn't have to use function-based indexes. I think in like modern development, it's not popular approach, and people most likely will add some Elasticsearch or add some Redis somewhere to work around this instead of like doing some magic inside the database.
This is the last question.
Yeah, just to comment on the last one, you can create like expression index. Like you don't need to actually create a separate column for you. You can like concatenate all the values together, create an index on it, and just use that.
Yeah.
Okay, time is over. Thank you very much for the talk, for the questions.